It's my pleasure to be here and have a chance to talk to you all and present my ideas about the mind. Today, I'm really going to present sort of a vision. It's not a complete worked algorithm, but and it sort of can't be because it's got some prerequisites, and the prerequisites are not available yet. And so prerequisites are basically a working deep learning algorithm, an algorithm that will be able to continually learn and improve the way it learns over time. It's a small ask, I always thought, but it's something we strangely don't have yet in our family of algorithms. Okay, so before I start, I just want to mention among my many jobs is I founded something called the Open Mind Research Institute, where we do basic research on reinforcement learning related approaches to the mind. And if you're a young person interested in something in that area, you might want to check us out at openmindresearch.org. Okay, so let's get started. Basically what I want to talk about is my quest for a simple general architecture for an AI agent. And I'm going to spend some time talking about the goals and how basically we want learning from experience in a very big, complex, unknown world. And then we'll get into the OaK architecture itself. And I'll have several ways of talking about it, explaining it, pictures, 4 pictures, and go through it step by step and talk about this vision. So it's like the holy grail of AI, of AGI really, is to have a quest for mind that's a little bit hard to look at. Let me just get rid of the background. A vision of mind that's general. And by general, I mean it contains nothing specific to any world. So there's no domain knowledge. And secondly, it's experiential. We learn from runtime experience and not from a special training phase. So runtime experience is in red because in the diagram, I don't know, maybe you can see my cursor. These things in red, the observation, the action, and the reward, those are the experience. Experience is unlabeled information, uninterpreted information, because we have we're seeking for a general design. And so there's nothing specific to the world. The observations are just bits, distinctions, and you have to, through your experience, make sense of it. And finally, perhaps most important, is the idea of open-ended abstraction. We want the agent to develop concepts, ways of thinking, common patterns in its behavior that are unlimited in their sophistication, then of course by their computational resources. So abstraction tends to really be of 2 kinds, just to help you think about where I am. Abstraction is like finding features of the world, features of your understanding of the world that are helpful to you. Features, I mean cues, ways, concepts, a way of organizing that a signal that you form in trying to understand the world that then you use to help you make your decisions. So you can search for good features, which are sort of like state, and it's good. The good adjective to add to feature is a state feature. And then the second thing we want to find is good temporal abstractions, things that you could do that are at a larger scale than a single action. So like abstractions like walking to work, or opening the door, or picking up the object. Okay, so we'll talk all about that. That's the quest. And I talk about it's useful to have these 2 words, design time and runtime. Design time is when an agent is designed and before it's sent out into the world to obtain its reward. And at design time, you build in domain knowledge into the agent. So of course I'm going to minimize that. I'm going to deprecate that. Runtime is when the agent is learning from experience and making plans that are specific to the particular part of the world that it's encountering. I'm going to emphasize that, runtime, learning from experience. Now, in a big world, in a big world, a complex world where things can't all be fully anticipated, then building things in a design time alone is insufficient. And in particular, if you are interested in open-ended abstractions, then you have to be able to discover them at runtime. They cannot have been only anticipated ones, non-open-ended ones could have been built in at design time. Really, we have to discover things at runtime. Everything has to be done at runtime. So if everything has to be done at runtime, really, why don't we just not do any of it at design time, because it will just complicate the design. So the design is, you might want to think of it as a way of understanding intelligence rather than as a way of producing a product. So for producing a product, you might want to build in a bunch of information, a bunch of background knowledge. But for understanding the mind, you want it as simple and pure as possible. And so for understanding it, you don't want to leave out all those complications. Okay, I'll say a little bit more about that right here, in fact. So I'm saying that this agent architecture, an ideal one for this goal, understanding intelligence, should make no design time commitments to any particular world. From my bitter lesson blog post, as I say there, the actual contents of minds are part of the arbitrary, intrinsically complex outside world. Arbitrarily complex. Their complexity is endless. They should not be built in. Instead, we should build in only the meta methods that can find and capture this complexity. So we want AI. We want AI agents that can discover like we can, not which contain what we have already discovered. And that's the basic idea and why we deprecate domain knowledge in the name of generality. Okay, so let me ask you a question. Should the agent learn from special training data, or should we restrict ourselves to only learn from runtime experience? And for me, the answer is clear. I think this is what the power of intelligence is, and particularly the power of reinforcement learning, is that we can learn from unprepared runtime experience. So let me just be clear about my commitment. My commitment is that the agent should only learn from runtime experience. And that's what I mean when I say the agent should be entirely experiential. Okay, and I mentioned the big world perspective. So here's our agent, like the person, and it's smaller than the world. In fact, it's much smaller than the world. The world has all those other agents. Maybe it usually looks like this. The world contains all the objects and places and complexities of the physical world. It also contains a myriad of other agents, and what's going on in their minds is totally important for the agent. The agent's correct behavior is interacting with people, its boss, and its spouse and its friends. What's going on in their minds matters to them, just as what is going on in your minds now matters to me. So the implications of the world being much, much more complex than the agent, and inevitably so. Yeah, nothing the agent learns can be correct, can be exactly correct. It can't be optimal. It's just any theorem you have that has to do with optimality or correctness, really, you have to know that it's irrelevant to the real situation. All your value functions must be approximate, your policies must be approximate, your state transition models, particularly your model of the world, has to be much simpler than the world. So it's going to be wrong, it's going to be approximate. Even a single state of the world, you can't really keep in your head, because the state of the world includes what's going on in all those other agents' minds. And of course, what's in your mind can't be much more complex than all those other minds. Okay, another implications of this, a little bit more advanced, subtle, is that the world will appear to be non-stationary. Because you don't know exactly what's going on in it, it's going to appear to sometimes be one way and then sometimes be another way. Just like if you're driving down the street and you see the car ahead of you, you don't know whether that car will turn right or turn left. I mean, it's not random, really. Whatever in the head of that agent who's driving the car ahead of you is maybe deterministic, but it's going to appear non-stationary. And sometimes the car will turn one way, and sometimes the car will turn the other way. It'll appear to vary. So with all these effective uncertainties about the world, you have to learn at runtime. You have to plan at runtime. You have to be able to find any needed abstractions at runtime. You're going to be born and grow up and encounter the world, and you'll have to figure out what are its objects and its people and the ways that the world works, and the way the social institutions work. You'll have to figure all that out at runtime. You can't be designed in, so we deprecate that. Okay, so let's get going now to the OaK architecture, which is addressing all these things. Let me approach it. Just talk about the general AI problem. It's to design an effective, purposeful agent that acts in the world. And in reinforcement learning, it's the same problem, except we formulate it in a particular way. We specify the purpose as a scale in terms of a scalar signal called reward. I'll say a little bit more about that in a minute. And secondly, perhaps in special to reinforcement learning, we assume that the world is general and incompletely known. So the world could be anything from a grid world to a complex human world, stochastic complex, non-Markov, nonlinear. And its state space, as I've said, is effectively infinite, and its dynamics is effectively non-stationary. We have to work at runtime. We have to apply at runtime without some special training signal from a teacher or human. And this is a problem. Is great. I think we don't need to change it. The reward signal is enough. We just have to solve it. And I also want to mention that I'm going to assume that the agent is limited by compute, not data. The data is rich. And we want streaming algorithms so that we will exclude things like replay buffers. Now, I've said the purpose is specified by a scalar signal. I want to spend another slide on that. This is what's called the reward hypothesis. The reward hypothesis is that all of what we mean by goals and purposes can be well thought of as the maximization of the expected value of the cumulative sum of a received scalar signal that we call reward. And I think this is not a limitation at all, but this is in fact just a great, clear way to specify the goal, and adding additional things doesn't make it better, would not make it better. And there's been some theoretical work on this, and I encourage you to check out this paper by Michael Bowling and others on settling the reward hypothesis. And also we know that even a simple reward can lead to all the attributes of intelligence. And maybe I shouldn't say we know that. I and others have argued that in a sufficiently complex world, a simple reward can lead to all the attributes of intelligence. That's the reward is enough paper. Okay, now let's get started, the OaK architecture. And I like to start with a prior architecture. And this is what I call the common model of the intelligent agent. And it's common to many fields. It's common to AI and psychology, control theory, economics, neuroscience, operations research. Everybody uses this standard, uses a model of the agent that has certain basic attributes. Number one is the red things, the experiential interface, the fact that you have reward, the fact that you have action, the fact that you have some kind of signals from the world that are your observations, and the fact that the observation, in general, the observation is not sufficient to totally disambiguate the state. So that's the outside view, those three things, the red things. Then the other, but really the common model, much of it is about the inside things and the four components, okay? First look at what interconnects the components. What interconnects the components is the blue thing. It's the state feature vector. It's how you represent the state of the world, and it's a feature vector, so it has components, and each component is a feature. And this state feature vector is created, it's basically your understanding of where you are. And so when you create this sense of where you are from your input and past actions, that a good word for that is perception. It's how you perceive the world and represent where and represent where you are now. And it's the basis on which you, for example, pick your action. I'll assume you can see my cursor. Here, this state representation flows through, and it's the input of your action. Your policy will reactively, which means without much deliberation, it will pick an action. So those are the first two components, the perception and the policy, and they together make up a full agent. But in order to learn that agent, to improve it, you want to learn a value function. The value function says, oh, I'm doing well now, or I'm doing poorly now, things have gotten better or worse. So it has to know the rewards, because the value function is essentially a prediction of reward. And that's used to learn the policy, which we suggest by doing this diagonal line through the policy structure. And the fourth component is the transition model, which we use for planning. The transition model, it basically takes the states and it tries to predict the next states if you act in a particular way. And I can't show all of how it works, but in one way or another, by the process of planning, we have a diagonal line through the policy, and again, we change the policy. And we also change the value function in both these cases. Okay, that's the common model. We start, does learning and planning, has these four components. And I think it's kind of interesting that we can take this single view to cover all these different fields. Like control theory will use different names. It won't talk about action, it'll talk about controls. It won't talk about reward, it'll talk about payoffs or costs. And psychology, for example, we might say reward, but we would, instead of saying observations, we talk about the stimulus. And so anyway, all these fields really have the same ideas, sometimes with different names. Okay, so, and we have to ask the question, what is missing from the common model? Why aren't we done? And the key thing that we're missing is that it's kind of, it's low level. The actions are the momentary actions. The reward, momentary. The observations are momentary. We have to get higher level abstractions. We have to develop concepts. We have to develop ways of thinking that are at a higher level. And so basically, I think what we need to add, and what the OaK architecture tries to add, is open-ended abstraction to this view. Okay, so here's the OaK architecture, and I've tried to show in purple all the things that are new. Okay, it's this OaK architecture, and it's adding auxiliary subproblems. So subproblems that are auxiliary to the main problem. The main problem is getting reward, and the subproblems, well, we're going to see this phrase a couple of times. They are reward respecting subproblems of feature attainment, which means they are about, each subproblem takes a particular feature and tries to attain it, but it respects the reward. It says attain this feature while still, getting a good amount of reward and not suffering too much in terms of your reward. The picture here looks almost the same. The policy, now we have behind it a bunch of more things that are called options, and they are like further policies. And behind the value function, we have more value functions. So we have a whole bunch of value functions. Of course, we have to have one value function for each subproblem, because it's a separate problem, and we have to know how well we're doing with respect to it. And so we need more value functions. So now we have four kinds of components, because, well, these two are the same, but these two are now multiple. We still have perception much the same, produces a state feature vector, which will be used by all the subproblems. And now the policy, we also form all the options, and they produce a way of behaving that's appropriate for the subproblem. And value functions, many value functions for evaluating how well we're doing on each subproblem. I don't show the subproblems here. It's interesting. You don't actually need an object in your architecture for the subproblem. You just need to have the value function and for it. And this pulling off little tendrils of the feature vector represents the idea that we are each value function has a separate feature that it's trying to optimize. Okay, now let's dwell on just for a second on the transition model. The transition model is what I'm going to use the word knowledge for. Anything that's, all of our knowledge is in our transition model, how we believe the world would change if we did different things, and in particular, if we did these larger things called options. Let me talk about that now. So the name OaK, the OaK architecture, comes from options and knowledge. And an option is this higher level way of behaving, but it is just a pair of a policy and a way of terminating. Just those two things grouped together. A policy is just a map from the states to the probability distribution over the low-level actions. And the termination condition is just a map from the states to the probability of terminating. Now in OaK, we have a lot of these options. Well, like one for each feature, each numerical feature, and then it learns the knowledge about what will happen if you followed that option until it terminated. So that's the form of knowledge. You'd have, things like, if I picked up the object and held it in my hand, what would it feel like? If I walked downstairs and looked in the kitchen, who would I see there? If I traveled to Iceland, what kind of people might I meet? If I attend the talk, what will I learn something? That is your knowledge about what will happen. It becomes a high-level transition model of the world that enables planning to look at larger jumps and hopefully carves the world at its joints. So the OaK architecture involves these 8 steps that we'll be talking about. They're all done in parallel at runtime. I'll be talking about them bit by bit, but you might just look at them. I'm going to learn policies and value functions, maximizing reward. I'm going to generate new state features. I'm going to order the features. I'm going to create the subproblems, one for each highly ranked feature. Then I'll learn solutions to the subproblems. I'll learn transition models for the solutions of those subproblems. And then I'll plan, and I'll have to maintain metadata on the utility of everything. Okay, so hopefully some of those words made sense to you. Let's go through it step by step and assess, are we able to do it now? So the first step of learning the policies and the value functions for maximizing reward, well, that is classic reinforcement learning, and we have millions of algorithms for doing that. But still, I'm not going to give it a green check because I don't consider it totally solved. It would be solved if we could really do continual deep learning well. And as I said at the beginning, this is the major prerequisite that we don't yet have. So let's look at that. So here I'm just going to focus on that first step for a moment, and noting that it requires reliable, continual, deep learning. And can we do this yet? I mean, because we've needed to do this for at least 40 years. And I've always been, or I am rather disappointed that no one's figured out how to do reliable, continual, nonlinear learning. We can do it for linear networks. Linear networks can learn reliably and continually, but conventional deep learning, fails catastrophically once we ask it to continual learning, to maintain its learning ability. So most famously, we get catastrophic forgetting. This is going back to the 90s, and more recently it's come to the fore, the fact that we just lose the ability to keep learning. This is called loss of plasticity, and it's been shown by other folks in my lab and in others. So, and one of the solutions, maybe we have partial recent solutions. We can do deep learning and learn continually, somewhat, continual backprop. Another idea that might help is continual discovery of new features and step sizes. And I do believe that one way or another, we will get reliable, continual, nonlinear learning in the next few years. And so I think it's sort of fair to assume that it will come along and to rely on it existing, as I do in the OaK architecture. Okay, going back, that's the second step. We need to generate new features from existing state features. So here I'm not talking about finding the best ones. I'm talking about generating a bunch of candidates. Okay, so I think this is not really clear. This one, there are lots of ideas. Let's talk about this. So OaK will require the discovery of new state features. And it's an old problem. It's going back to the 60s. You're probably familiar with it if you have been around. It has many names. So the whole idea of representation learning, or the new terms problem, or meta learning is often used for this idea. And this is what backprop was supposed to solve. This was supposed to solve, but really does not. What was the paper? Learning representations by gradient descent or something like that was the original backprop paper. And there were some papers sort of claiming that it does, but I think nowadays we acknowledge that it doesn't really find good representations, except in the desperate sense that it eventually solves the problem, and that may require some representations, but it doesn't generalize well, particularly, and it really isn't finding the representations. Other methods have been based on generate and test. Again, things going way back into the past, like try a bunch of candidate features and then select the one, just see which ones generalize better and keep those. And the continual backprop again is one of these new algorithms based on generate and test. And so this I'm holding out is really an unsolved problem. We need to do it. We need to have a good way of generating new state features from existing features, and I'm going to rely on it. I have my own personal favorite idea for solving this problem, which is the IDBD algorithm. And I think that's going to be part of the solution. So I'll give you the name here at the bottom of the paper if you want to check it out. Okay, next, we've got all these features that we've created, candidate features that we've created, and we want to rank them. And this, I think, seems easy. It's easy to rank them by are they proving useful to the subproblems and to the agent and to the learning of the model. All you can just see are the features being used and use that to rank them. So you can rank them, and then the big problem is, or the big substantial step is to create the subproblems, one for each highly ranked features. So I want to talking about that because I actually think this is easy to do, and we have done it. So how do you create subproblems? Well, first I have to acknowledge there's a long history, again, of people working on auxiliary subproblems, and there's some issues that are largely settled, and there's some issues that are still open. And so let's talk about the open questions. Open questions like, what should the subproblems be? Where do they come from? Can the agent generate its own subproblems? And how do the subproblems help on the main problem of getting reward? And OaK, the OaK architecture, offers answers to all these questions. So subproblems, I think, are what we're looking at in play. And if you just think about the life of an animal or even a human, then our life is full of subproblems. But here is a young orangutan, and I think he's focused on the subproblems, just the sensation he gets when he swings. He's trying to enjoy that and reproduce it. So can he get that to happen again? What does he need to do to get it to happen? You can think of what the play that he's undergoing here as is trying to obtain that feature, the feature of swinging, his vestibular system saying what that feels like, which is something that doesn't normally happen to him. Okay, similarly, here is actually an orca, sometimes called a killer whale, who's in an aquarium, and someone's thrown this float in with him, and he's been playing with it, and he's found out that he can carry it on its back. It's just sort of an interesting thing that he noticed that he could do, and then he, without being trained at all, he learned how to do it reliably. So this is what I think this play is, and we can think of it as being focused on obtaining a feature. Here's a human example. Here's an infant playing, and its behavior is not random. Its behavior is sped up a little bit. I'm sure you noticed. But it interacts with the toy, it learns some things, And then it moves on, you know, when it stops being able to learn more to look at the next opportunity for learning. And so um, this is what we call curiosity, of course, but we can think about it as having subproblems of feature attainment. Certain experiences it can have, colors or feelings or sounds, and it's trying to be able to reproduce them. It's one way of thinking about the process of exploration and curiosity in terms of subproblems. It's gaining control over its world. Okay, so obviously, an agent must create its own subproblems. There's no way for all the possible subproblems to be built in. The infant encounters its world and sees what's available to be done, and then it learns how to attain the things that are there. So the possible subproblems are too various and they're too world dependent. We have to give the responsibility for forming the subproblems, for posing the problems to the agent. And we have a lot of the necessary algorithms for doing this. We have options. We have the idea of value functions in its full generality. We have off-policy learning and planning methods. And so we have to create subproblems in a domain general way. And so how could you do that? I mean, what possibly could they be a subproblem? And I think I'm going to offer the solution, this reward respecting subproblems of feature attainment. And the best rationale for it is just that there's really almost nothing else one can think of other than attaining the features. You know, you can't talk about states because the agent doesn't have states. You can't talk about objects in the world because we don't have a priori objects in the world. All we have is the features and concepts, which are concepts, which we have formed to understand the world. Okay, so if we haven't checked my timing too much, I do wonder how I'm doing. If I have time to go through the specific way we create subproblems in OaK. Basically,
Yes,
we start
please.
with a feature.
Please do,
So
yes.
that is an index, a feature number, like feature 53. And kappa is how intensely you want the feature that you have to specify. If you specify those two things, we can automatically have a subproblem. The subproblem is to drive the world to a state where the feature is high without losing too much reward. And so the solution is an option. It's a policy and a way of terminating that maximizes the value of the ith feature at termination while respecting the rewards and value. So you want to maximize, you want to choose the option so as to maximize the expected value of the total reward you'll get during the option, some of the rewards from the current time, because it's all conditional. I'm starting at time t in the designated state S. And then we start following the option and we'll get some rewards. And we'll end at time capital T. And so we're interested in the rewards received between those times. And we're also interested in the value of the resultant state. We don't want to be left in a state where bad things are going to happen. So this is our estimated value of being in that terminal state. And this is the feature attainment. Of course, we want, and when we stop at time capital T, we want to be in a state where the feature phi I is high, so that value is large, and it's multiplied by kappa, which is how intensely you want the feature. So these are reward respecting subtasks of feature attainment, and there's a paper on this in AI Journal a year before last. So that's what I think the subproblem should be, and we then have to learn the solutions and learn the models of the solutions. The solutions are the options. And so these two things, I think, are relatively straightforward, but again, they are rely on us being able to do continual deep learning well. But if you grant me that prerequisite, then we can do it. And so this is where we really get to the heart of OaK. So just pay attention to the overall structure of the argument now. And basically, we're going to do all these learning processes, and they're going to use features, and they're also going to drive the creation of new candidate features. So basically, we're going to have features, and that carries over here. Once we have features that are interesting, we can create subproblems to achieve each one. So once we have those subproblems, we then solve them. If we have 1,000 subproblems, we would solve them to produce 1,000 options. Okay, each one of those options will then be the foundation. We ask the question, if I did that option in this situation, what would happen? So that's the transition model. We're predicting the consequences of behaving in that way. Now, this is different than, solving the problem is finding a good way of behaving. And that would be a way which hopefully achieves the feature. But there will be many other consequences of behaving that way. You may achieve the feature, you may, other things will happen. If I go downstairs to the kitchen, I may get to the kitchen, but I might also see my spouse, or I might trip and fall down the stairs. Many things could happen, and I need to predict the possible consequences. So that's the transition models, and then once I have the transition models, I have to use them to plan, which improves my behavior and will hopefully get me highly adaptive behavior. Okay, now let's look at the same with a different picture. So we're talking about perception, giving me the features. So now I've got the state features, then I solve those subproblems, I play with the world, and I get the options. The options I predict the consequences of the options, and that gives me a transition model. The transition model through planning gives me improved values and policies. And then all of these later steps feed back and they inform perception. We tell perception, oh, in order to form this model, I had to use some features and not use other features. In order to solve the problem, I used some features and didn't use other features. So these processes inform the feature construction process, and they could say, oh, these features that you've offered me are useless, and you should throw them out and get me more features. And these other features are very useful. Maybe they should be the basis of future problems, subproblems that are posed and solved, and thus recursively improve in an open-ended way the abstractions of the agent. Okay. So I need to say a little bit about planning because it's one of the key steps. So and planning is a big topic, and I'm going to give it the green check because assuming we have the models, I have a specific plan for planning, a plan for planning. Well, first, why do we plan, and why do we want to plan with sort of these large-scale steps, jumpy steps? We want to plan because the world changes, and because the world changes, our values change. Another way of saying it is it's easier to get the model right than the values right. So at any point in time, if the world changes, the values change. Finding my way to the restroom is really important, but the value for being in the restroom changes. Sometimes I want to go to the restroom, sometimes I don't. But the model of the option for getting me to the restroom, I want to retain that even as I change in my desires about whether I want to go there right now. So it's as if, the values of the states change, most of the world dynamics remains the same, and to prepare for this, you have to get ready, and this has implications. But let me just go into planning, just to give you a rough idea of what I'm thinking of. The idea of value of planning is that it will be done by value iteration, in which you improve your value function so that you know which states are good and which states are you want to be in or don't want to be in. Which features do you want to attain? Do you want to be true? Now, this expression in classic value iteration, and what's for the equation written here is classic value iteration. Classic value iteration is expressed for the case of discrete states where you could have a table where you can store the value of each state. So we'll do this. I need to do this case first in order to understand the idea. So in value iteration, continually, all the time, when you have spare time to think, what you do is you select a state, And how you do that is an important question. And then you perform a backup at that state. So the backup of the state will improve the estimated value of that state. And you take a max over all action, all the things that you might do, and you want to look at the reward that you expect to get. R hat is your expected reward. Okay, this is from your model. Over here in the upper right, we have the model. What is the model? The model of the world, it's two things, R hat and P hat. And the model takes a state and an action and guesses what will be the probability distribution over the next state, and also what will be the expected reward. Those are the two. This is what a primitive model does. It's not a high-level model. This is a primitive model. Value iteration is defined for primitive models, low-level models. Okay, so you have the expected reward, and then you have basically the expected value of the next state. You're summing over the probabilities of each next state and the values of that next state, discounting it by a little bit. You're basically sitting here at this state S, and you're looking at all the actions you might do and all the states that might result, and then you sort of figure out what's likely to happen, and you back it up and change the value of state. And all planning methods have the same idea within them. Some of them, this is value iteration looks exactly like this, but even things like A star and Monte Carlo tree search and model predictive control, they all involve the basic idea of looking ahead and seeing the consequences using your model and updating your sense of the value of your different states or different choices, and then making your choice according to them. So this is value iteration. And then when we make it abstract so that we can make jumps, we can make large steps in the world. That's the next step. Okay, so life is lived one step at a time, but you plan your life at a higher level. You plan to go to the talk. You plan to stand up. You plan to go to the restroom. So this model, the knowledge, your transition model, this is the transition model, which I'm calling knowledge. It's about these large-scale dynamics where your actions, where your choices, which are options, are purposive. So our knowledge is not conditional on single actions. It's conditional on things like, calling an Uber to get to the airport and traveling to Iceland, or going to the restroom, or picking up the object. So these are larger ways. These are knowledge about the options. And so the option model, this is the conventional model repeated from the last slide, and we generalize that to an option model. We just replace action with option. So the input is all things that I might do, these extended ways of doing, and I get, it's not the next state, but it's the state at which I will stop or terminate when the option stops. And instead of the expected reward on one-step reward, I have the expected reward that's summed over from when I started to when I terminated. Okay, but with those two changes, the valuation is the same. We have the same sum over possibilities, and we get the reward and the expected value of the state of stopping now, and it's the same idea. Okay, so we can do planning at the abstract level using value iteration. And the other thing that I need to do is I need to provide some insight into how we generalize this to handle function approximation, because the world is big and we don't have a V of S. We don't have a value for each state of the world. But we have a value of each state of the world, which is determined by our weight vector, by our parameters. So this we can have. We have some approximation. The state of the world will be presented to us in our observations and our feature vector, and then that will be involved with our parameters and give us an approximation. Okay, and so of course the model will also become parametric. We will predict the reward along the way, and also the transition probabilities to the next states at termination. Those will also be parametrically represented. And so instead of doing this conventional thing with the table, we're going to do we're going to update the weights, and that's shown down here by a gradient procedure. This thing in here the thing in brackets, this is replaced. So we have the reward, expected reward is now based on a model, and a transition model, and a parameter of that model, and the transition probabilities are based on the parameter. And then we have the estimated values. So this backed up value is analogous to the thing in brackets. And so that becomes the target. So here we move the estimated value for the state we're looking at, S, is moved towards the max of the backed up value for the for our choices. Okay, so we've gone back to primitive actions now to do the function approximation. This will also generalize to the full option case. Okay, so I have to move on and finish up, and so I can take some of your questions. The very last step is to acknowledge that everything needs to be. We need to keep statistics or metadata on the qualities of everything, the quality of the transition models, because the model will be approximate, and we have to learn where it will give me reliable answers and where it won't. We have to keep statistics on the features so that we can inform the feature generation process about when it's doing, which features are good and which features are bad as it generates new features. So with that, I'm just going to wrap up. Oh, I have one more figure to remind you, to give you a sense of what it is. One more time, OaK is open-ended because it has its cycle of discovery, and this is the ambitious new idea of OaK, that is to be open-ended in its possible abstractions, limited only by compute. And the basic cycle is this cycle. We start with the state features. From those, we construct subproblems. From subproblems, we solve them to produce options. And the options, we then can produce models of the options, which improve the options and the policies through planning processes. And all of these steps, these three steps here, will use the state features. And so so the arrows go in one direction, but really there's a influence the other way, which is we're informing the state features, which ones are useful and which ones are not useful. So that involves the ranking. And then, so that will lead to, oh, here's a new feature that I didn't realize was really important before, but everyone's making a high use of it. This is a good concept. And then that concept, that feature becomes the basis for a new subproblem. And that's really what makes it open-ended and possibly getting better and better abstractions through time through this cycle. But everything is ultimately tied to reward. So remember the quest. The quest is to be general, experiential, and have open-ended abstraction, which I think maybe, I hope you can see this vision gives you a way you might hope to achieve all of these things, even though it has some missing prerequisites. So OaK has a vision of how to grow superintelligence from runtime experience. It has all the most important capabilities. It can act, learn, and plan. It can learn a model. It can form subproblems, these abstractions, different things to work on, and the options. And it can do this with function approximation, partial observability, non-stationary worlds, stochastic worlds. It can discover state features and thereby discover the subproblems, options, and models. And this all feeds back to motivate more abstract features, this virtuous open-ended cycle of discovery. While at the same time, the architecture is completely general, it doesn't have any domain-specific components, and thus is scalable and of potentially lasting impact. Thank you very much for your attention.
Thank you very much, Rich. It's wonderful to have you here. Of course, congratulations on your recent Turing Award, and thank you for all your contributions to the field, and of course to reinforcement learning. Hopefully you can also help us with this robust, continual, deep learning as well. And we have a few questions from the audience if you have time. So we have one over here.
Yes, looking through your list of requirements there for OaK, I noticed that in the chimpanzee example, the orangutan example you used there, it seems like the create subproblems for highly ranked features can consume the second and third states because you already have a reward function built into the mechanism of the chimpanzee to enjoy the swinging, let's say. So it's some sort of chemical reaction that then says this is a highly ranked feature because of your experience. And so the generating state functions comes from the formation of the system itself in its embodiment of how it gets rewards from the environment. And then that rank ordering then becomes that like the benefit of the reward rather than necessarily a taught K, to your point of biasing features. So I guess my question would be, is there a way to maybe skip steps between 1 and 4 by assuming that subproblems come from play based on generated, fun, let's say, in your terms, to say, well, the thing that is getting the reward is tuned to get that reward by the function of how it's built.
Well, see, you're rightly focusing on how we select features to become the basis of subproblems. Now, some of that can come from our prior design. Like our design may say bright lights are likely to be important, or loud sounds. And maybe our design can tell us that things that activate our vestibular system are important. But many things are not like that. So, you think of your work in science, you study a problem and you become aware of very subtle distinctions, and you still might want to focus on them and work towards them. Or maybe you play chess, and you have things that are superficially subtle, like the structure of your pawns, and then you can make a goal, or the safety of your king. You can make goals for that. So I don't think you can anticipate. You can expect them to be anticipatable. But it could come about by you just noticing that these subtle things are important for answering some of your questions. And they could be useful for answering your basic reward questions, or it could be for answering other subproblems. So maybe a good example is to think about an infant, and the infant becomes very aware of its caregiver. Let's say its mother, and I don't know, maybe the smell of its mother is a subtle thing, but it be through association with good outcomes, it becomes important. Or the sound of their voice, or the sound, yeah. I also think of the example of playing with a rattle. Maybe you move and you make the sound of a rattle. The rattle is some particular sound, but it's novel, and just because it's novel, you might want to focus on it and be able to reproduce it. Anyway, it's a wonderful, interesting question of how the subproblems become chosen. Thank you for your question.
Thank you. One more here.
Yeah, hey, this is Ben. So we've had a few talks at this conference on predictive coding as an alternative to backpropagation for training deep neural nets. And I know there's some research going on trying to use this to solve the catastrophic forgetting problem and make neural nets able to continuously learn. So I guess my question is your intuition that the continual learning problem can be solved using backpropagation, or do you think we'll need to go to backprop DC or some other perhaps more biological or else other innovative way of doing the training of neural nets?
Thank you, Ben. I don't think it's a problem with neural networks, the structure of neural networks. I think it's a problem with the weakness of simple backpropagation. The solution and the solution, I think, will still involve gradient descent, but the gradient descent alone is not enough. This is sort of the lesson of the continual backpropagation algorithm. But this is the new algorithm that was proposed by Dohare and studied in the loss of plasticity paper. That it's a simple thing. It's just the same as backprop, except instead of initializing with small random weights only at the beginning, you do it as you go along. A small fraction of the units that are not being used very much are reinitialized with random weights. So this is a very simple idea, a simple modification. It's actually just making backprop more continual, making it doing more of what it already does. And so it's a small modification of the algorithm, which makes it vastly much more capable of continued learning. And so I think the space of algorithms is large, and we have just done so little to explore it. And there'll be small or maybe larger, but anyway, there's a wide range of possible ideas to make it more effective at continual learning, and they will involve still gradients. It's just the gradients alone
predictive coding also involves gradient descent. You're just learning it, using it for different things. I mean, you're doing gradient descent at one neuron to predict what some other neuron is doing locally, but so you're not propagating the same way as in backprop, but you're still doing gradient descent locally. It's more like in the direction of Bengio's difference target propagation, but a little more extreme, right? So yeah, as you say though, there's a lot of ways to organize it.
The key thing is that you need a random component. You need a search component. Gradient descent is deterministic and follows the gradient. That's not enough. You need something that will generate variety. This is what the initialization with random weights generates variety.
That's a good bit of wisdom. I would agree. A random component is going to be one of the critical elements. So yeah, thanks for that.
Thanks, Ben. And we have another question at the back of the room.
Hello. I had a question about how continuous observations on the world get turned into new possible actions, how that sort of process occurs. Like if the child's playing around and they discover this heavy thing that's a hammer that they can pound on stuff with, and slowly they discover nails and boards, how does using the hammer to put the boards together come into being in your learning mechanism?
Now you said continuous, and continuous has two possible meanings. I just want you to clarify which one you mean. Continuous could mean like it's a number that takes a continuum of values, or you might mean that it's ongoing in time.
Yeah, I'm referring to the ongoing in time, just creating new possible actions that you can take based on observations. Is there a reification that turns into an abstraction of here's a tool I can use? How does tool use get discovered is I guess what I'm asking.
Well, that's a big question.
Yeah.
But
even
yes,
like a simple tool like a hammer.
I would offer that this has us as a hint of how it's done. Let's see, how would so you would find, maybe you find the hammer and you realize you can use the hammer to make a noise. So you could become skilled at making a noise with this hammer. And then you might, what I'm pointing out is that you're hammering in a nail is a pretty advanced concept. It's a advanced skill, and you won't expect it to be successful right away. But you could use the hammer to make noise. And then you could use the hammer to break things. And probably in order to become skilled at hammering a nail in, you'll have to watch someone else do it. And if you watch someone else take a nail and a hammer and do this really interesting thing where the nail went into a board. You know, that's kind of a unusual observation. And that could be the basis then for, you know, can I use the hammer to get a nail to go into a board? Okay, and then one could work on that for a long time. And then once you had that, you would, you know, maybe you would have the idea that you could, you know, assemble something by the tool. I don't know. That's a bit hand wavy, but I think there's a progression from detecting interesting novel features and wondering if you can reproduce them. And so then, you know, the key is that you just want to be able to hammer it, even though it's not getting you reward. You want to make you want to reproduce something that you saw it being done, rather than, even though it doesn't get you any reward immediately, but you learn how to, and you also learn how to hammer the nail into the board without hurting yourself. For example, without hitting your thumb with the hammer. That's the sense in which you want to be reward respecting.
Thanks.
Thank you.
Thank you very much. One last question.
Hi. How do you think a new agent will go about discovering and understanding the boundary between itself and the world? Like, what is itself and what's the environment?
Well, I think it's kind of interesting how that blurs. Because when you're, well, where is the boundary? First of all, you know, where would I draw it? I would draw it around your mind, which you might think of as around your brain. So in particular, your body, like your hand, is part of the environment. It's something that you can't control completely, and you're interested in controlling. And you know, we can think of how a child doesn't initially know how to control its hand or its other limbs. And you could see a young infant, in fact, you know, will often just look at their hands and figure out how they can control them. And, you know, first you can find them, like, you know, hey, here's my hand, and I can see that. Now I can't see it. And I say, well, hey, can I get that? It doesn't say, here's my hand. It says, here's an interesting sensation. Can I get it to happen again? Can I bring my hand up to my field of view? Can I get my thumb back in my mouth? Here's an interesting object. I wonder how it would taste if I put it in my mouth. So there isn't, where's the boundary? And that reminds me to say something, because it's often unclear to folks who haven't been doing reinforcement learning for a long time, about the reward. The reward comes from outside the agent, but it doesn't come from outside our body, right? The reward is computed inside our head, in fact, inside our brain, but it's a part of the brain that is not considered part of the agent, because the agent is not allowed to just set its reward to be high. There's a part of our hypothalamus, I think, that computes the reward signal, and that is technically outside the agent, just as the body is outside the agent. I have to, of course, refer now to the extended hypothesis, how as we get more familiar with controlling something, like our body, it becomes it becomes more useful to think of it as part of the agent, you know, or as we driving a car, we start to think of the car as we're controlling the wheels, and the wheels are like our choices. And this is changing the abstraction, and it is a useful way to think of it. But formally, we want to have a clear line between the agent and the environment, and a clear definition of the primitive actions that are available before we introduce higher level abstractions. Thanks again.
It's wonderful. Thank you very much, Rich. Such a clear explanation. Great discussion. I don't know if you can hear the applause, but we really appreciate you being here and joining us today. Thank you very much.
Thank you very much.